transpose A is a terrible idea. Just like computing A inverse, well, that's even worse. But this is also something you want to avoid. And the reason why is you get a loss of information. Due to whatever round-off error you incur in computing A transpose A. Because every entry, there's a round-off error. So what's desirable to do is to try to solve, if you have any matrix algorithm or solving a system or doing something else with it that involves A transpose A, you want to avoid computing A transpose A explicitly. Instead of modify your algorithm so that it works only with A, or A transpose, without actually performing the multiplication. And this is something we'll see at the end of the semester, because we'll learn how to compute eigenvalues, and then to get singular values, that's like finding eigenvalues of A transpose A. And we're going to do that without ever computing A transpose A. And it turns out there is a way to solve normal equations without actually computing A transpose A. You solve this system instead. So we use a block approach where we have identity, A transpose, and 0. It's our matrix. Our solution is R and X. And our right-hand side is B, 0. Okay. Now, if I were to write out what these equations translate to, so that's the same as R plus AX is equal to B, and then A transpose R is equal to 0. So this goes to what I've done earlier for normal equations, because R, from this equation, R is equal to B minus AX. That's what we want. A transpose times the residual is equal to 0. And that residual is end up being required to be B minus AX. So this actually gives us the solution X to the normal equations, and then R just turns out to be B minus AX. So here, I can go ahead and solve this system. I can use whatever approach, but I never have to actually compute A transpose A. But I am solving a system that's double the size, but at least we have two very simple blocks here, identity and 0. And it turns out this kind of structure, where we have a symmetric positive definite matrix here, these two blocks are transposes of each other. There's a name for this kind of matrix. And actually, one person might have a good chance of knowing what it is.
Saddle point.
Yes, it is a saddle point matrix, as opposed to the non-symmetric saddle point matrix you've been working with. But yeah, when these are transposed of each other, this is a saddle point matrix. Okay, actually, now, the saddle point matrix, saddle points come up in multivariable calculus. We're trying to find maxes and mins, but in higher dimensions you can sometimes find saddle points. You have a minimum when the Hessian is symmetric positive definite, like a second derivative being positive. You have a maximum when the Hessian is negative definite. So in those cases you have all positive eigenvalues or all negative eigenvalues. A saddle point matrix, saddle point happens when you have the Hessian being indefinite. It has both positive and negative eigenvalues. And it turns out that a matrix like this is actually going to have both positive and negative eigenvalues. So that's where the name saddle point comes from. And actually, I did not remember back from looking it up. I just figured it out on the fly. Because now I was thinking, like, what if this is just a matrix of numbers? Well, the sum of the eigenvalues would be 1. And the product of the eigenvalues as a determinant would be something negative. So we have a positive and a negative eigenvalue. And it probably might be easy to express the eigenvalues of this in terms of the eigenvalues of A, but I wasn't going to figure that out in my head. Okay, but it's probably where the term saddle point comes from. When you have a function that is increasing in some directions and decreasing in other directions, the graph has the appearance of a saddle, so that's what they call a saddle point. Okay, so this is one important point to make. We don't want to form A transpose A. Now, another important point to make about the normal equations. Regardless of whether you're solving it directly or you're using this approach, there's one very unfortunate thing, and that is the condition number in the 2 norm of A transpose A, well, that's going to be, that's the norm of A, that's the norm of matrix times the norm of its inverse. But in a 2 norm, that's the same as the largest singular value of a matrix divided by its smallest. Now, when the matrix is symmetric positive definite, the singular values are equal to the eigenvalues. That's the only time that happens. So I can replace it with that. Well, the singular values of the eigenvalues of A transpose A are the singular values of A squared. So this turns out to be the largest singular value squared divided by the smallest singular value squared. But that's going to be the condition number of A in the 2 norm squared. So this is the unfortunate thing about the normal equations, and actually with least squares problem in general, is that whatever system you're solving, it's going to have a condition number that is the square of the condition number of A. So it tends to be a lot more sensitive. And that's one reason why people avoid solving the normal equations. Although it turns out that for certain least squares problems, the QR factorization is generally preferred. It's usually more numerically stable, but it's actually not dramatically better. Okay, so it really depends on. So the guideline is if if A is m by n, where m is much, much greater than n, in that case you're probably better off using the normal equations. But if it's a closer to a square system, you're probably better off using the QR factorization. Okay. Right, so this is one unfortunate thing here. We have this extra sensitivity. Okay. Let's see. I don't need that. Okay. Now, yes.
Will you say that again about if?
Oh, when to use which approach?
Yes.
Yeah. If A is, okay, we're already talking about the case where A is m by n and m is greater than n. So in other words, a tall, thin matrix. If it's really tall and thin, so m is much, much greater than n, you're probably better off using the normal equations in that case. Because the QR factorization tends to be most sensitive in that case. On the other hand, if you're closer to having a square matrix, so for instance, maybe you're solving a system, a least squares problem, where it's the matrix is n plus 1 by n, something like that. QR factorization is probably a better approach in that case. It's not a hard, fast rule. It's a guideline, and the reason for this guideline is if you look at section, so for more about sensitivity of the least squares problem, 613 in the notes talks more about that because it shows how the error in the solution depends on the condition number of A. In fact, it often relates to the condition number of A squared.
Thank you.
All right. Let's see how we're doing on time. Oh, okay. So what I can do is at least start on methods for actually computing the QR factorization, and then I'll continue with that on Wednesday. Alright, so approaches to computing QR factorization. There are Gibbons rotations. There are householder reflections. So both of these are matrix transformations and they involve orthogonal matrices. These will be very useful tools for us when we go to compute eigenvalues later on. And then the third one, which is actually not as good as these two, but it's very well known. It's for a thin QR factorization. It's called Gram-Schmidt orthogonalization, which you may have seen in some other classes. I know it comes up in 415, for instance, where you're just taking a set of non-orthogonal vectors, like the columns of A, and you're making a set of orthonormal vectors from them. Well, those are the columns of Q, or Q1, really. And I won't really get into this one because numerically, it's an awful method, and it's really bad compared to these two. But just to make the connection in case you've seen it before. Okay, so I will spend what time is left today getting into Gibbons rotations. Now, in fact, Gibbons rotations, though used by Gibbons, were not invented by Gibbons. They're actually invented by Jacobi. We use them for a very different purpose than what we're going to deal with. Okay. So, now, the idea behind a Gibbons rotation is this. So given, pun not intended, I swear, you have a vector x that has these two elements, a1, a2. So you want to find an orthogonal 2 by 2 matrix G that has this form, C minus S, S, C, such that G transpose times X has the effect of zeroing the second element. And then the first element will be some number R. Now, R is going to be the square root of the original element squared. Also, in order for G to be an orthogonal matrix, we need G transpose G to be identity. So in fact, we have C squared plus S squared is equal to 1. And then in fact, what it means is C and S form a cosine sine pair. So C is equal to cosine theta for some theta, and S is equal to sine theta